A bridge in a graph theory problem would be described to be an edge in a connected graph without which the graph would be disconnected. So it's sort of like a vital connecting edge that is, if you don't have it, your graph falls apart. So like if we're looking at this graph, we can kind of think we have one little section over here and another section over here, and there is an edge that connects those two, right? And I can imagine if I was to delete the edge DF, that graph would become disconnected and we'd have two disjoint segments. And a bridge, it's like if we think about the term, it's often like in the real world, what a bridge does is you're connecting an island to a mainland. Like think of the Coronado Bridge. Well, if you don't have the other strand, but often we build bridges to connect things that are not connected. And like technically there might be a secondary bridge, or you might have two or three bridges which connect land masses together. The point still stands as to what's the idea. So in graph theory, technically it has to be the only connection. And if you were to build, like say for example, we imagine this is one island and this is a second island, right? We build a bridge to connect them together. That's kind of the idea. But notice that if we were to build a second bridge between two points, technically neither one would be a bridge in graph theory anymore, because each individually, if we had two, neither one is the only connection, right? So if I did have edge EJ, let's go ahead and pretend that that graph had that, and then I were to delete edge DF, technically the graph is still connected, so neither one of those would be a bridge after the fact. But anyways, that's the idea behind a bridge, and again, this is a term that is referenced later in later chapters. And specifically, other terms that are going to be used a lot are the terms path and circuit. And actually, I already used the term path previously because it's kind of intuitive, but let's go ahead and examine the graph theory definition and talk about why it matters. So in graph theory, it says a path is a set of distinct adjacent edges. So distinct is something that's important to not overlook, but and also what is this saying? And it says it's adjacent edges. Well, remember what adjacent edges were really meant was they're connected. So if we take a collection of connected edges, that forms a path. Or if you think about what a path means, say for example, I was trying to get from A to K in the form of a path, you could kind of obviously figure out, well, I'm trying to get from one point to one point. Like for example, I could go A to D, D to F, F to H, and H to K, which would be a path solution. And one way you could write a path is by listing all of the vertices, A, D, F, H, K. Sorry, I really don't like writing with my mouse, so excuse the horrible notation. But what I wanted to do is explain how do we write a path. In the graph sense, we could just visualize it by highlighting it, which is one common method that we use when we're solving problems in the next few chapters. But we could also list them by listing the points in order. ADFHK would describe that path, and its length is just how many edges are in that path. So in that case, it would be 1, 2, 3, 4, or it would always be one less than the total number of vertices, right? Because if we have 5 vertices, each, the starting vertex didn't really create a path, right? It was like going from A to D, that's 1. Then D to F is 2, F to H is 3, and then H to K is 4. And anyways, or we could do it from A to J as the example suggests, but doing it from A to K is fine. So, but notice that there's technically not necessarily one path. That was one option for a path, but there's so many more. That one was the most efficient path because it used the least number of edges. It had the shortest length. But you could have a longer path. Say, for example, went A to B, B to E, E to C, C to D, D to F, G to I, F to G, G to I to H, and H to K, and that would be a much longer path from A to K. And you might wonder, well, what's the longest path from A to K? And these are all questions we could answer. These questions aren't really relevant to the problems that we're going to be studying, but you can think about why these would be relevant. And if we're trying to be a security guard and we want to go to every path, you can see why we would look for longer paths and why that might be relevant. But also, you might wonder, well, is there a longer way of doing that? Like how, and how could I actually figure that thing out? Like, for example, what I could have done instead was go like A to B, B to E, C to E to C. But what you might have thought to do was maybe I could go then C to B, then B back to A, A to C, C to D, or something like that. And that would obviously make the path a lot longer. But technically, this is not a proper path because of the term distinct. So notice that in this hypothetical route that I'm inventing here, I've actually used the edge AB more than once. And so this would not be a path. This would technically not be proper due to the fact that I've used the same block twice. And to return back to this first video, this is what we call deadheading, which is something that we're often trying to avoid in these chapters because we typically don't want to traverse the same stretch twice. Now, in some problems you might, but for the sake of efficient street routing, or say we're trying to photograph a neighborhood, we don't want to do this, and that's why it's not part of the defined term for path. And same with circuit. And these are not obvious things, and that's why I wanted to mention, what this is getting at as well. And so the term circuit I've already mentioned, but basically it's the same exact thing, but it's a path that starts and ends on the same vertex. So if you think about A, instead of going from A to K, which would be a path, let's say we were going to go from A and we wanted to create a path that comes back to itself. And that's, what a circuit generally means, right? Is a loop, right? Like a car, a NASCAR circuit or whatever. You're coming back to the same point and you're doing it over and over and over again for whatever reason. And notice, like in a security guard problem, a lot of times we'd be looking to form a circuit because, say, for example, we're starting at a point like our office, and we wanted to go patrol the neighborhood and come back to the start. That's usually the goal. So you can kind of imagine sometimes you're thinking about paths between different points, but other times you're thinking about circuits. And notice that that would be one example of a circuit in this graph. A to B, B to E, E to C, C to D, and then D back to A. And you might be thinking, well, could I make a larger circuit than this or a smaller circuit? Yeah, I could obviously do a smaller circuit, for example, A, B, C, A. And notice how you would write it would be much the same way. If you're trying to write it using just the vertices, you could do it like that separately from the graph, or just highlighting it on the graph is fine as well. And a lot of times we like to put arrows, or we'll be putting arrows on our graph just to indicate which is the direction of this path or circuit as well. But anyways, and that would be a circuit of length 3. Again, it's one less than the number of letters in the list. So you could think of, well, is there a shorter circuit? No. And also, what about trying to do a full circuit? Like, what if I wanted to go across every edge, or say I wanted to go over here and run through a circuit on this side of the graph. Notice that, again, since it's technically a path, it's technically a set of distinct adjacent edges. So in a graph that has a bridge, there is a big problem, which is why there's a relevance of a bridge. Because once I've gone across the bridge, technically I can't go back because it has to be a set of distinct adjacent edges due to the deadheading condition. So with the terms path and circuit in a street routing problem, or in when it pertains to graph theory, this is a problem. And if I'm trying to formulate a circuit, basically I can't cross a bridge because I'm going to have to return back over it at a later time.